today we're going to be talking about gas laws. This PowerPoint is by Tori and Nicki.
Yo yo!
Okay. So, pressure is a very important component of gas laws because pressure is involved in many of the calculations that you have to do. So pressure is the continuous physical force exerted on or against an object by something in contact with it. A common property of gases is that it exerts pressure on its surroundings. And when calculating using the gas laws, you most likely will need to convert between pressures. Here are the pressure conversions. 760 milliliters of mercury equals 760 torr equals 1 atm equals 101.3 kPa or kilopascals equals 101,325 pascals. So pressure can be measured in a couple ways. Here are a few. The barometer measures atmospheric pressure. Evangelista Torricelli filled a glass tube with liquid mercury and inverted a dish of mercury. The pressure exerted by the atmospheric gases on the surface of mercury in the dish keeps the mercury in the tube. The second way of measuring pressure is with a manometer for measuring gas in a container. It also contains mercury.
Okay, so now we're going to talk about Boyle's Law. And he is an Irish chemist, Robert Boyle obviously, and he used a J-shaped tube closed at one end. And which is shown over here in the illustrations, and he studied the relationship between the pressure of the trapped gas and its volume. So pressure and volume have an inverse relationship. As one increases, the other decreases. Okay. So Boyle's law, PV equals K, is where K is a constant for a given sample of air at a specific temperature. The most useful form of Boyle's law is P1 times V1 equals P2 times V2. Where P1 is the initial pressure, P2 is the final pressure, V1 is the initial volume, and V2 is the final volume. So, here are some examples of Boyle's Law. We're going to write up here. So, the first example shows that a 1.53 liter sample of a gaseous SO2 at a pressure of 5.6 times 10 to the third pascals. If pressure is changed to 1.5 times 10 to the fourth pascals at a constant temperature, what will the new volume be of the gas? So let's write our givens. So we have a volume 1, which is 1.53 liters, and then a pressure 1 of 5.6 times 10 to the third pascals. And volume 2, we don't have that. That's what we're looking for. So that's going to be a question mark. And pascals 2, or pressure 2, is 1.5 times 10 to the fourth pascals. So let's set it up like how we have it here. We have P1, which is 5.6 times 10 to the third pascals, times 1.53 liters is equal to the volume 2 times 1.5 times 10 to the fourth pascals. So to get volume by itself, we have to divide by pressure 2. 1.5 times 10 to the fourth over 1.5 times 10 to the fourth. So volume 2 is equal to 0.5712 liters. And if we're looking at sig figs, we need the least amount. So this has 3 sig figs, this has 2, and this has 2. So we're looking for 2 sig figs. So the volume of 2 is 0.57 liters. For Boyle's Law, example 2, we have 4.35 liters of a gas that is at 1.16 atm. And we're looking for the pressure, which is obtained with a volume of 9.3 liters. So let's write our givens. Volume 1 is 4.35 liters, and pressure 1 is 1.16 atm, and volume 2 is 9.3 liters, and pressure 2, we don't know what that is, so we are looking for it. So now 4.35 liters times 1.16 atm equals 9.3 liters times pressure 2. And remember, we have to divide to get P2 by itself. And look, our liters cancel out on each side, and that all cancels out. So our P2 equals 0.5425 atm. And converting this to sig figs, we have 3 here, and 2 here. So we only need 2 sig figs, which will be 0.54 atm. And that is our answer of pressure of 2.
The next law is Charles' law. French physicist Jacques Charles found in 1787 that the volume of a gas at a constant pressure increases linearly with the temperature of the gas. The volume of a gas is directly proportional to the temperature. The law in this case is V equals BT, with T being the temperature in kelvins and B equals the proportionality constant. The temperature conversion from Celsius to kelvins is adding 273 to the temperature when it is in Celsius. The most useful form of Charles' law is V1 over T1 equals V2 over T2. V1 equals initial volume, T1 equals initial temperature, V2 equals final volume, and T2 equals final temperature. Here are some examples of Charles' law. So the first one says a sample of a gas at 15 degrees Celsius and 1 atm has a volume of 2.58 liters. What volume will this gas occupy at 38 degrees Celsius and 1 atm? So the first thing that we are going to do is write the law. So Charles' law is V1 over T1 equals V2 over T2. So next we are going to identify our values. So 15 degrees Celsius would be T1. V1 would be 2.58 liters. And T2 would be 38 degrees Celsius. And we are going to find V2. So, to rearrange our formula in order to find V2, our formula will look like V1 times T2 over T1, and that will equal V2. So notice that the temperature is in Celsius, and we previously said that we need to convert temperature to kelvins. So to do that, we'll do 15 degrees Celsius plus
gonna be in there.
plus 273, and that will equal 288 Kelvin. So that is T1, and then T2, when we convert, would be 38 degrees Celsius plus 273, which will then equal 311 K. Now, we will plug in our values to find V2. Next, we are going to write down our values. So T1 will equal 288K. V1 will equal 2.58 liters. T2 will equal 311K. And V2 is what we are finding. So, next we plug in our values into the equation. So, V1, 2.58 liters, times T2, 311K, all over T1, which is 288K. This will equal 2.7860 liters, but we need to round for sig figs, and our sig figs will need to be 3, so we will round to 2.79 liters, and that is the value for V2. So example 2 for Charles' law. We're going to read it and then identify the values. So 5 liters of a gas is collected at 100 K and then allowed to expand to 50 liters. What is the new temperature of the gas at a constant pressure? So first we identify the important parts in the problem. So 500 liters is V1, 100K will be T1, and then that gas is allowed to expand to 50 liters, which would be V2, and it's asking us to find the new temperature, which will be T2. Now let's write down our givens. So V1 is 5.00 liters, T1 is 100K, V2 equals 50 liters, and T2 is what we're solving for. So next we're going to rearrange the equation to find the new temperature. Unlike in our first problem, we will not need to convert from Celsius to Kelvin because our temperature is already in Kelvin. So, the equation, when rearranged, will look like V2 times T1 over V1 equals T2. So, let's plug our values in to find T2 now. So, V2 is 50 liters times T1, which is 100K, all over V1, which is 5.00 liters. And that, when plugged into a calculator, all equals 1,000 K. Next we solve for sig figs, and in this case we will have 3 sig figs. So the value of T2 will be 1.00 times 10 to the third K, and that equals T2. Next, we're going to go into
Gay-Lussac's law. And in 1905, the French scientist Joseph Louis Gay-Lussac established that hydrogen and oxygen combine to form a volume ratio of 2 to 1. In 1808, he discovered the law for combining gases. The pressure and the temperature of gases are directly proportional, so as one increases, the other also increases. You must use kelvins for the temperature, while pressure is typically in the form of atms. The most useful form of the law is P1 over T1 equals P2 over T2. So the initial pressure is P1 and the initial temperature is T1. The final pressure is P2 and the final temperature is T2. Here are some examples of the law. So first we are going to write these laws. So remember that it is P1 over T1 equals P2 over T2. So for number 1, 10 liters of a gas is found to exert 80 kPa at 42 degrees Celsius. If pressure is compressed to 40 kPa, what is the new temperature of the gas? So even though earlier we said pressure is typically in the form of atms, if they're both in kPa, then it's fine to leave it in kPa. So, yeah, they just need to both be the same pressure. So let's find our givens. So we're looking for pressure and temperature. So we don't need liters of gas, but we have pressure 1, which is 80, and temperature 1, which is 42 degrees Celsius. And we have pressure 2, which is 40 kPa. But we unfortunately don't have temperature 2, which is what we need to look for. However, our temperature is in Celsius and we need it in Kelvin. So we are going to do a conversion first. So, 42 degrees Celsius plus 273 equals Kelvin. So our Kelvin equals 315 K. And we have all of our other givens, so let's write them down. So our pressure 1 is 80.0 kPa. Our temperature 1 is 315 Kelvin. Our pressure 2 is 40.0 kPa, but we don't have a temperature 2. So let's plug it in to our equation. So 80.0 divided by 315 equals pressure 2, 40.0 over question mark, because that is our T2. So, what we will do now is rearrange so that our question mark is all by itself. So that means we multiply the 315 up here, so it'll turn into 80.0 equals 315 times 40.0 over question mark, and we multiply this question mark up here. Or some can say that this is cross multiplying. So now our equation turns into 80.0 times the question mark, which equals 315 times 40.0, and that's kind of off the page, but that's okay. So now we have to divide by 80.0, and our question mark, which is our temperature 2, equals 157.5 K. And if we're looking at sig figs, we don't really go off of temperature, so we're going to be using 3 sig figs, which our T2 is 158 K. And there is our answer. Now for example 2, we have 467 liters of a gas collected at 34 degrees Celsius and 300. For example 2, we have 4.76 liters of a gas which is collected at 34 degrees Celsius and 635 millimeters of mercury. If the temperature is increased to 67 degrees Celsius, what is the new pressure of the gas? So we have one temperature here and another here, and we also have our pressure. And we need to find our other pressure. But see how our temperature is in degrees Celsius? We need to convert that to Kelvin first. So our temperature 1 is 34 degrees Celsius plus 273 equals our Kelvin, which equals 307 K. Our temperature 2 equals 67 degrees Celsius plus 273, which is our Kelvin, and that equals 340 K. And our P1 is 635 millimeters of Hg, and our P2 is a question mark. Now let's put this in the equation. So our P1 is 635 millimeters of Hg, and that is over our T1, which is 307 K. And that is equal to our P2 over our T2, which is 340 K. We must multiply 340 K up here to get rid of it. So 340 K, those get crossed out, and we're left with our P2. And this equals 703.257 millimeters of Hg. And if we're looking at sig figs, we are using 3. So our P2 is 703 millimeters of Hg. Next we will be talking about the combined gas law. And this is where you're kind of combining Charles, Boyle's, and Gay-Lussac's law. So it is P1 times V1 over T1 equals P2 times V2 over T2. So P1 is the initial pressure, P2 is the final pressure, V1 is the initial volume, V2 is the final volume, T1 is the initial temperature in kelvins, and T2 is the final temperature in kelvins. So here are some examples. So let us write our equation up at the top. So we have P1 times V1 over T1 equals P2 times V2 over T2. So for the first one, we have 3 liters of a gas collected at 35 degrees Celsius and 705 millimeters of Hg, which is, so we are trying to find the volume at STP. When it says STP, that means standard temperature and pressure. So we're looking for the volume. So pressure is 760 millimeters of Hg. Okay, so standard pressure is 760 millimeters of mercury, and temperature in Kelvin is 273 K. So we know that is our pressure 2 and our temperature 2, and we need to find our volume 2, or our finals. And we have givens for the initial, which is 3 liters, 35 degrees Celsius, and 705 millimeters of Hg. However, we see that this is in Celsius. We need to convert this to Kelvin. So, for our initial pressure, our P1 is 705 millimeters of Hg. Our temperature, 135 plus 273 equals 308 K, and our volume 1 is 3.00 liters. Now we are going to plug this into our equation. So P1, 705, times our V1, which is 3.00, all over our T1, which is 308, equals P2, which is 760, times V2, which is question mark, all over T2, which is 273. Now to get our question mark, or our V2 by itself, we need to multiply this 273 up here, so this will be 273, and we need to divide our 760 to down here. So we're really doing this, 273 over 760. And this will give us our V2. So when you multiply 273K times 705 millimeters of Hg times 3 liters over 760 millimeters of Hg times 308K, you get volume 2. So our volume of 2 equals 2.4666 liters. But if we're looking at sig figs, we have 3 here and 4 here. So we'll be taking 3 sig figs. So our V2 equals 2.47 liters. There you go. And so for number 2 over here, you can see that we already are given all of our values, and we're really looking only for P2. So we're just going to plug it straight into the equation. So we have 30.0 ATM times our V1, which is 47 liters, over our T1, which is 50 degrees Celsius. But since these are in degrees Celsius, we need to add 273 to make it into Kelvin. So this will be 323K and 27 degrees Celsius plus 273 equals 300K. So 30.0 ATM times 47 liters over 323K equals P2 times 55 liters over 300K. We're going to do the same thing where we where we multiply and divide these two. So multiply by 300 over 55 times 300 over 55. So those cancel out, these cancel out. And so our P2 is going to equal 23.81 ATMs. And since we have 3 sig figs, 2 sig figs, and 2 sig figs, we'll be using 2 sig figs. So our P2 equals 24 ATM. For number 3, it asks, what is the temperature of a gas when it is compressed from 200 torr to 150 torr? So we have our P1 and our P2. And let's just write that down right now. So P1 equals 200 torr, and our P2 equals 150 torr. And its volume is increased from 40 liters to 60 liters. So that is also our V1 and our V2. So V1 equals 40 liters, and our V2 equals 60 liters. And now, you can see that the initial temperature is 55 degrees Celsius. So T1 equals 55 degrees Celsius plus 273 which give us our kelvins. When you add 273K, you get 328K. And that is our temperature 1. And our T2 is what we are looking for. So let us plug these values given into our equation. P1 is 200 torr. V1 is 40 liters. This is all over our temperature 1, which is 328K. And that is equal to P2, which is 150 torr, times V2, which is 60 liters, all over T2. So, we are going to cross multiply like we did previously in a different slide. So these will be multiplied here, and this will be multiplied up here. So we will end up getting T2 times 200 torr times 40 liters equals 328K times 150 torr times 60 liters. Now we're going to divide to get torr by itself, or to get we are going to divide to get T2 by itself. So we're dividing by 200 torr times 40 liters. 200 torr times 40 liters. Those cancel out, those cancel out. Torr cancel out with torr. Liters cancel out with liters, and now you're only left with K. So T2 equals 369K.
So to wrap it up, we're going to talk about some important vocabulary that is from this section. There are other vocabulary words that were mixed in the PowerPoint. These are just the most important parts that we really want to drill into your brain. So,
Into the brain.
Constant is a controlled variable, a theoretical experimental quantity, condition, or factor that does not vary in specified circumstances. For example, we are keeping pressure constant. So this is also an example. We could tie in like the gas constant to this, which is what we used for the ideal gas law. And yeah. So next is temperature, the degree of hotness or coldness of an object. For example, the temperature of the water on a hot day was 30 degrees Celsius. And again, remember that in most of these calculations, you will need to convert from Celsius to Kelvin. So you just add 273 to the Celsius to convert it to Kelvin. Next is volume, the amount of space occupied by a solid, liquid, or gas. An example of this is the volume of a bottle of Coke is not 591 milliliters, which is how we ended up doing this PowerPoint. The next vocabulary word is pressure, which is a force exerted by a substance per unit area of another substance. An example of this is the pressure of Mrs. Luckett's room is approximately 765 torr. So, again, thank you for listening to our PowerPoint, and we hope you learned something.
You better have.